Hey everybody, it's that time again. Here, quick video chemistry topic. What's on tap today is little ionic bonding. So what is ionic bonding? What's involved in it? Well, it is always a metal and a non-metal together. And always when you have a metal and non-metal together, pretty much based on their periodic trends, the metal has all those trends as like, take my electron. The non-metal is like, no problem, be happy to do that, because non-metals pretty much like to hang on to their electrons and bring electrons towards themselves. So when these two always get together, we actually get a transfer there of electrons from the metal to the non-metal. The result of that is our metal loses an electron, becomes an ion. That is known as a cation, which is positively charged because frankly, it has lost an electron. Our non-metals picks up some electrons, also becomes an ion known as an anion, which are negatively charged as a result of gaining electrons, basically. Remember, in ionic bonding, there is absolutely no sharing of electrons. So there is no sharing of these electrons. You're getting an actual transfer of electrons. What actually holds an ionic bond together is what's known as electrostatic attraction. It's a fancy way of saying opposites attract. Remember, in chemistry, opposite charged things are attracted to each other. Things with the same charge do not want to be near each other. So it is actually that attraction of the positive charge to the negative charge that's holding that bond together. And that's what an ionic bond is. How can we represent ionic bonds? Well, in bonding in general, we usually represent them with what are sometimes referred to as Lewis dot symbols, named after a guy by the name of Lewis, I would imagine. Lewis is big in bonding. If you're watching this, you probably know that already. Nowadays, though, sometimes people just generically call them electron dot symbols as well, and they're basically the same thing. So what is it? Well, when we're talking about bonding, there's really two types of electrons that we have in an element. We take lithium, for example, electron configuration 1s2, 2s1 has 3 total electrons. These guys here on the first energy level, these are sometimes referred to as core electrons, not involved in bonding. So core electrons, because they're close to the nucleus, they're held tightly, they're not involved in bonding. It is these guys over here, that's on this example here, second energy level. These are known as the valence electrons. And the valence electrons are the outermost highest energy electrons. Yes, sir, they are involved in bonding. So when we're doing bonding, it's always the valence electrons. In the case here, lithium, it is one valence electron for lithium. Who wants to write electron configuration to figure out valence electrons? Good news is you don't need to do that. You could go to this wonderfully drawn periodic table here. And if you look on the periodic table and you look at the group numbers, the number of valence electrons equals the group number. So everybody in group 1, like our friend lithium here, has 1 valence electron. Everybody in group 2, 2, 3, 4, 5, 6, 7, and 8. One exception is our friend helium. Helium only has 2 because, frankly, it only got 2 valence electrons and it's only got 2 total electrons. So it does not have 8. Everybody else in group 8, your neon, your argon, your krypton, all the ons there in group 8 will have 8 valence electrons. Helium will only have 2. Hydrogen has 1 valence electron, and because it only has 1 electron as well. So when we look at Lewis dot symbols, a much easy way to figure out the valence electrons is just to look at the group number. Whatever the group number is the number of valence electrons that you have. Good news is in most cases our transition metals, which are here, not really involved in bonding. You probably won't come across it. But by the way, it also equals the group number for our transition metals, the valence electrons, except you would probably want to use the secondary numbering, the 1, 2, 3, 4, 5, 6, all the way to 18 numbering. But really for transition metal, kind of 3 through 12 numbering is probably what you would want to use if you're looking for valence electrons for your transition metals. There is what they would equal. That's because they have the S's and they also have the D's available to them. So they have a little bit more valence electrons than our representative, which is sometimes referred to as the A numbering, the one to skip the transition metals 3, 4, 5, 6, 7, and 8. So back to Lewis dot symbols or electron dot symbols. We draw them by taking a symbol, basically one dot to represent each of the valence electrons that an element has. As you can see here, there's basically 4 sides. 4 times 2 is 8 electrons, and that is the maximum you could have. In most cases, not really too much of a rule on this, except usually we don't go more than 2 per side. So a lot of times people will kind of do 1 per side, and then maybe, kind of pair them up, if you will. So something like lithium would look something like this. It's got 1 valence electron. Something like aluminum has 3. So it may look like this. Something like fluorine is just group 7, has 7 valence electrons. So maybe it looks like this. We got carbon, which is group 4. It's got 4 valence electrons. So these are all Lewis dot symbols, or electron dot symbols, that's used for both ionic bonding and also covalent bonding, which we might cover in another quick lecture later on. But right now we're just going to focus on ionic bonding and really what's happening in ionic bonding. So let's take a look at what happens when we make an ionic bond between a metal and a non-metal. So we can actually take our friend lithium, which has 1 valence electron. By the way, it's electron configuration 1s2, 2s1, as we talked about. And if you're not sure about electron configuration, there's another quick video lecture there on electron configuration. Maybe we'll put a link up here. You could go to it if you like. Let's say we put that together with our friend bromine from group 7, which will have 7 valence electrons. Again, if we sort of wrote the electron configuration here for bromine, I'm going to do sort of the shorthand here, so I don't have to write a bunch there. That's argon. We got 4s2. We have 3d10 and 4p5. And in the case of bromine, it is our 2 and our 5 here, which are 7 valence electrons. They are in the highest energy levels, the 4th energy level there. Over here, it is our 1 valence electron there. So what's going to happen in this case? Well, because this is a metal and a non-metal, our lithium is going to want to get rid of its electron. It's going to send it over. And in this particular case, what's going to happen is our bromine will accept it. It's really at this point, and by the way, these do not have charges on the left-hand side here. It is at this point when lithium loses its electron, it now has a charge and becomes an ion. The bromine says, thank you very much, and will pick up that electron. That's now going to give bromine 1 extra electron and a negative charge. Just going to put a little bracket around the bromine. And now we have an ion for our bromine. And we now just made an ionic bond. What's holding that together is absolutely no sharing of electrons, which is why when you draw these Lewis dot symbols for ionic bonds, you still need to show the charges, as that will indicate there's no sharing of electrons here. It is that opposite attraction, that electrostatic attraction, that's holding that together. And that is basically the formation of the ionic bond. What happens for each of these ions? Well, let's see. Our lithium here has lost this electron. Now, in this case, has an electron configuration of 1s2. That is 2 electrons. If you take a peek at the periodic table there, number 2 is our friend helium. Now, when we look at bromine, bromine actually had a spot right there in the p subshell for those electrons, actually that one electron, and it will fill in right there, and it gives us now bromine here, our bromide ion, that now has electron configuration of argon 4s2, 3d10, 4p6 right there. That is, if we count it up there, 36 electrons. I'll do that math right there. 18 electrons for argon. 2 more makes 20, 30, 36. That is also the same electron configuration as krypton. So what just happened here? Well, we made 2 ions that now have achieved the same electron configuration as noble gases, making them super stable in this case. That is really the whole point of all types of bonding, ionic bonding, covalent bonding. The point of it is for everybody to achieve noble gas configuration. They do not become those elements. They're still lithium. They're still bromine because they still have the same number of protons. Remember, protons is what determines the element. But here they now get a much better electron configuration. They're stable like our noble gases, which are chemically inert. And that's what everybody's trying to achieve in bonding. They are what are sometimes referred to as being isoelectronic with a noble gas. So lithium with a +1 charge and helium are isoelectronic with each other. Bromide and krypton are also isoelectronic. Let's take a look at maybe another example here. Let's take a look at our friend magnesium. Magnesium is group number 2 on the periodic table. And it has an electron configuration 1s2, 2s2, 2p6, 3s2. There are the 2 valence electrons there in magnesium. Let's say we put this guy together with chlorine, group 7 on the periodic table. Electron configuration 1s2, 2s2, 2p6, 3s2, 3p5, 5 and 2, 7 valence electrons right there. So what's going to happen in this case? Once again, we have all the makings of an ionic compound here, an ionic bond. That's a metal, that's a non-metal, and frankly, that's all you need right there, those 2 things. So magnesium, again, because of its periodic trends, wants to get rid of those electrons. So it's going to send over an electron here to chlorine. That's going to find a spot right there. Problem though, chlorine is now full at that point. And that's going to be a problem for magnesium, because if magnesium only loses 1 electron, you look at the periodic table, that will basically just move them back to sodium, which is not a noble gas and not as stable as it wants to be. It wants to lose this extra electron or this other electron here. So in this particular case, we don't need just 1 chlorine to do that. We actually need a second, and a second chlorine will be able to accept that second electron. That's now going to move our friend magnesium back 1 more spot on the periodic table, not drawn the scale, and it's going to get them back to neon in this case. So what's going to happen in this case is our magnesium has now lost 2 total electrons because it gave 1 to each chlorine. That is these 2 electrons right here. Because it lost 2 electrons, it now has 10 electrons, 1s2, 2s2, 2p6. And as I said a second ago, that is the same electron configuration as neon. Now, this chlorine right here and this chlorine right here both gain 1 electron each. So let's just draw that. Couple dots there, there, and there. And -1 charge only because it gained 1 electron. I'm running out of room, so I'll just draw the other one here, even though they might not want to be right next to each other. but just for our purpose here, we'll draw it next to each other, and a minus there for our second chlorine. Looks like I got an extra dash there. We'll just get rid of that there. There you go. So what happens with our chlorines? Well, each chlorine has this configuration. So the first chlorine has a spot to put an electron there. And the second chlorine down here also has a spot, same spot there to put it. That's going to give each chlorine now 18 electrons. Each of those chlorines, which are now chloride ions, will gain 1 electron each and end up with a configuration of 3p6, or that is the same configuration as argon in this case. So all three of these things, the magnesium, this chloride ion, and this chloride ion, all achieved noble gas configuration. Again, very, very stable configuration. Truly the purpose of bonding. That is also, by the way, when you maybe have learned, when you take a positive ion and a negative ion and you put them together to write the formula for an ionic compound. The overall charge has to equal 0. So +2 -1 needs one more. -2 + 2 gives you the proper formula here of this. And that is really the reason why when we put together an ionic compound, the overall charge needs to equal 0. It allows everybody here to get that noble gas configuration and create a very, very stable bond. So what happens here with ionic compounds and ionic bonds? Well, what we've seen, metals, if you look at the periodic table, they will pretty much be group 1, group 2, probably group 3 over here. They tend to back up to our noble gases. So they'll go backwards by losing electrons and end up with the same electron configuration as the noble gas that comes right before them. As we saw with magnesium, it backed up to our friend there, neon configuration. As we saw with our first one as well, which I think was lithium, it backed up to helium's configuration, which is the noble gas that comes right before lithium. So metals will lose electrons and they will back up to the noble gas before them. On the periodic table, what happens with our non-metals? Well, our non-metals are right here. Our non-metals do the opposite. They actually gain electrons. They go forward on the periodic table to the noble gas after. So they go forward on the periodic table to the noble gas after them. So once again, what we saw there, I think we did chlorine. So chlorine moved forward to argon by gaining electrons. We did bromine as well. Bromine went forward to krypton on the periodic table to get to that noble gas configuration. So once again, that's the whole purpose really of all bonding, especially ionic bonding. So the way in an ionic bond that both parties there achieve stability is metals will lose electrons, become cations, positively charged, and back up on the periodic table to the noble gas before them. Non-metals will accept those electrons, become negatively charged anions, go forward on the periodic table to the noble gas after them. Everybody's happy, everybody's smiling, everybody's achieved noble gas configuration, everybody's really stable. That is pretty much ionic bonds. I hope it helps you. If there's anything else you want to know about in these kind of quick lectures, let me know in the comments. Otherwise, I hope you enjoyed it, and we'll see you on the next one. Bye-bye.